Welcome to Walkabout the Galaxy, the unpretentious astronomy podcast, where the science is universal, the opinions are personal, and we almost always know when we don't know what we're talking about. We are Strange, Charm, and Top, the astroquarks, also known as Josh Caldwell,
Addie Dove,
and Jim Cooney.
Coming to you from the Walkabout studio at the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. We are also on the World Wide Web at walkaboutthegalaxy.com, where you can see how to order a Walkabout shirt and support STEM education at the same time. Contact us at wtg@ucf.edu with any questions. And in the meantime, I'll direct a couple of questions to Charm and Top.
Yay.
That's us.
Actually, it's just one question.
Oh.
But it's to both of you.
Shared
Does that count as two questions? One to
stumper?
you and one to you, even if it's the same?
Is this a stumper?
It's a shared stumper. It's not really it's not a toughie. It's not a stumper.
Oh, it's just a question
It's
today.
just a question. Yeah.
Episode 251.
We ran out of stumpers. The
We're
first
just getting
250
questions.
stumper. From 251 on, it's just going to be like, what'd you have for breakfast this morning?
Okay, that's great.
What's your favorite kind of
breakfast.
galaxy? Spiral, elliptical, irregular, or dwarf? And why?
Oh.
Related to one of our science topics.
Okay. James, would you like to start?
I wanted to say irregular because it's like my digestive system.
I kind of had the feeling you would go for irregular, but I wasn't looking for that particular imagery.
No, I apologize.
It happens.
I'm going to go with spiral annular.
Ooh,
Excuse me.
More specific.
That also has to do with your digestive system, doesn't it?
Annular?
Spiral annular.
What if spiral annular?
Say it 10 times fast.
Yeah,
Oh, the reason I'm going for this, by the way, is currently in the Atlantic, the open Atlantic, is spinning Hurricane Larry,
I
Larry.
noticed that.
which is an annular hurricane currently. Annular
it comes
means
once a year.
No. Spiral galaxies are the flattened galaxies that have disks, and like our Milky Way has spiral arms, but annular ones are the flattened disks, but they don't have notable arms to them.
They're just a ring.
They're just kind of like a disc, a flattened disc, continuous disc.
Okay.
And Larry is doing that because it's in a fairly dry surrounding environment, which means its
It's
outer
in the middle of
arms
the
have a
ocean,
hard
Jim.
time firing convection.
I
Hey,
can
Jim.
tell you've been watching Tropical Tidbits or something.
Well,
Can you explain how in the middle of the ocean is a dry environment?
Yes.
yes.
It's that dry part of the mid-Atlantic.
Yeah, exactly. Well, the air
Atmospheric
is dry. Atmospherically
dry.
dry. The upper middle part of the atmosphere is dry. So anyway, it just reminded me of annular things. And annular,
Eclipses are a thing.
they are also. And
Yeah, it typically does
Larry
need a
looks a little bit
ring.
like an annular eclipse. It's got a big old eye and then a disc of, a ring of
Clouds.
mean stuff around it, and then nothing outside of that.
So I
And-
didn't know about annular galaxies.
Yeah, there are those as well that just don't have well-defined spiral arms, but they're basically spiral galaxies without the arm part.
They're not lenticular galaxies? Is that a different thing?
Yes.
Yes.
Okay.
I don't know.
I don't know.
Oh. Well, I guess this is an example of when we know when we don't know what we're talking about.
There you go.
So you like an armless spiral galaxy is what you're saying.
Yes.
Yes.
That is what he's saying. He's Googling
Now he's trying to
lenticular
figure
right
out
now.
if that's what he wants or not. What about you, Addie?
Oh.
No digestive tract metaphors, please.
Okay. I mean,
There's no such thing as an annular galaxy.
you just made that up.
Over. I swear, it was
Of
lenticular.
all the times
When you said
that I
lenticular,
said at the
That was the
beginning of
word I
a
was
show, we almost always know what we don't know what we're talking
said it,
about.
and I didn't
Of
know
all
what I
the
was
times for
talking
me to say that in an episode, this is the time where you just randomly make up a new type of galaxy. When in the stumper, I gave you a multiple choice.
You
I
did.
didn't say what's your
I did.
favorite
I
type of
didn't.
galaxy.
I
I said,
paused.
which of these four is it? And then you made up a fifth one that doesn't exist.
Yes. Yes,
beautiful.
All
You made up a
nice.
subclass that doesn't exist.
I did. I swore. That's what a
You've just
lenticular
been
galaxy
watching-
is, right?
A lenticular galaxy is lens-shaped.
Yeah, it's lens-shaped.
galaxy.
It's what I was thinking of, and then I had seen that Larry thing earlier today, and for some reason in my head, Because it's basically the same thing.
Well, I'm glad you gave an awesome class earlier today, though, because the podcast you're really kind of you're dying.
I'm all right. Today's
Are lenticular galaxies like?
Take a break. Go back and recoup.
Are non-spiral spiral galaxies like on their way to being elliptical galaxies? Are they like evolved? Are they?
There's some sort of discussion about temporal evolution of galaxies.
Yeah. There's that tuning fork.
Right, that Hubble diagram.
Hubble diagram that's not real.
In any event. Okay, regroup, Jim, while we hear what kind of galaxy Addie likes.
I mean, spiral galaxies are so pretty.
They are. They're prettier than elliptical galaxies, I think. They're more interesting.
Dwarf galaxies, though, are like pretty fascinating because they're just these little dudes that hang out in interesting places. Yeah. But probably spiral because they're pretty.
I'll go with that.
Well, yeah. What would you answer?
Irregular.
Why?
Because those are usually ones that have had some kind of
interaction event.
Collision or something like that, where one galaxy's plowed through another one, and it looks pretty cool.
Jim's figuring out how to teach Galaxies, the Galaxies class next semester.
Well, that
Josh
my
and I will do a
unintended,
podcast.
my post-stumper question, which actually turned out to completely stump Jim, could not have been a stumperless question. In any event, today we'll talk about ultra-diffuse galaxies, which is a kind of galaxy.
Yeah.
And a new study of the likelihood of a largish object in the distant reaches of the Kuiper belt. But first, this episode of Walkabout the Galaxy is brought to you by thermal inertia. Ooh. For those cozy evenings at home in front of a warm, crackling fire, or those summer afternoons with a touch of sea breeze to cool the heat from the setting sun, lock in your perfect temperature with thermal inertia. Also known as thermal effusivity. Keep your effusiveness in check as you disregard its ridiculous units with a square root of time and dial your thermal inertia up to the maximum to keep your temperature from changing. Then let your mass inertia keep you in that comfy recliner while your thermal inertia means you'll never have to reach for that sweater or turn on the fan. Thermal inertia melts in your mouth, not in your hands.
That sounds lovely. M&Ms.
Yep.
I would love to have some M&Ms in my hand while I'm comfortably resting in a recliner at the right temperature.
Yeah. And they wouldn't be melting in your hands.
I know.
Yep.
That'd be great.
Because thermal inertia has the most ridiculous units.
It does.
There's a square root of seconds in there.
Thermal inertia units.
Is that what? And, we have for force is a collection of units. We call it a Newton. For what else do we have?
There's lots of units out there.
There are watts and joules, combinations of the fundamental units of mass. And but for thermal inertia, there's no name associated with it. And it's the one in most desperate need of a name.
It does. I think
I can't stand it.
Than tried to define a name for it. Than Putzig when he did Mars thermal inertia stuff. He tried to define a name for it for a while.
But
there's a lot of people that use that, that do that stuff. Beauty Quark messes with that stuff all the time. Asteroids. So if you think that many people do it, they would come up with a name for the unit.
It's usually just used as TIU.
Thermal inertia units. But then you have to say this like SI version of thermal inertia units or something. But it's really like in acceleration is meters per second squared. We don't have a name for that, but at least you can say meters per second squared. It's okay. But thermal inertia is joules per square root of a second times something else.
Joules per meter squared per Kelvin per square root of a second. Yeah.
That's ridiculous.
It's ridiculous.
But yeah, his proposal is that it's TIU or TU.
Oh.
Partly because that's just the thermal inertia unit, but also apparently because it's the original name for Mars in Old English.
Oh.
That's why it's Tuesday?
TU.
Yeah. I guess
nice. Very good.
Good connection,
link.
Jim.
Good connection. You're back on your game.
All right, we're back.
He's back. He's back from the...
That was exactly what I was doing in class this morning, like mixing one word for another word and then saying the wrong thing. It's like...
Yeah.
Lenticular was the word I was looking for.
Good job.
Let's move on.
Okay. Well, we found it. It all worked together.
Yes.
This is why it takes 3 quarks to make a podcast.
There you go.
And many fundamental other particles.
That's right. Space news. SS2, Spaceship 2 is grounded.
I saw that.
On their flight with...
Virgin Galactic.
Thank you. That's what I want. That's all I want.
I know.
Perfect.
On their flight with Richard Branson, they deviated from their airspace.
Yeah, it wasn't a safety thing, probably. It's just that they deviated from the airspace that the FAA had allocated to them.
Right, which could have been a safety thing if they had crashed into a 747.
Exactly. Yes.
Right.
Yes. Yeah.
Right. Is there any? Why?
There's an investigation.
The FAA is looking into it.
The FAA is looking into it. That's the question.
The party line talks about high altitude winds or something like that, but I don't really know.
Yeah, and I don't know how far it was.
The thing is, they have to steer that plane up.
Yeah.
Right.
The rocket. They have to steer it onto as vertical a trajectory as possible, following an initial horizontal launch.
Right. But it is true that winds are very high in the upper atmosphere oftentimes, although it's not very dense, and so it doesn't push that hard on the ship. They're out of the dense part of the air pretty quickly, but I honestly have no information about what happened. I don't know.
Yeah.
Yeah. We had some other space news you were mentioning, Addie.
There's some
Percy news.
So Percy got its first sample. There were some issues with. So Perseverance is supposed to do a bunch of sampling where it basically cores some rocks and then it caches them in these little tubes and then it seals the tube and then it's gonna at some point it's gonna make a little cache location, a pile of tubes on Mars. But it had troubles on its first ones. I think it was like where it was trying to dig was just too sandy. Basically, it was like
nothing stuck or something like that.
It wasn't coring, but they successfully got one. And they sealed it up.
So are they is this like a bore drill where they're pulling out a plug of rock? Mm-hmm. So it's like a piece of rock.
Case, yeah.
Okay. Mm-hmm. Instead of drilling a hole and scooping, they're
it's a rock sample. It's a core sample.
A core sample.
Rock.
Okay. Mm-hmm. Like when we think of ice cores or things like that from Antarctica. Mm-hmm. And they're caching a few dozen of these over the course of Perseverance's time on Mars.
Yeah.
Is Perseverance itself doing any analysis of that, or is it just
not of those
samples?
It's like saying, here's where it came from. It's probably measuring the rock next to it. You know?
It takes a picture of the sample. It does some sort of measurement on it, but they have been doing other analyses, of where the site it came from. So there's context for the site it came from,
and also presumably that's how they thought, oh, this is an interesting rock. I'd love to get a chunk of that back in my lab here on Earth.
Right.
And decide instead of just wandering around like I would do. It's let's pick up that rock.
Yeah. That's a pretty one.
Maybe we can get a core sample of that one.
Yeah. So they're in a section of Mars of rocky outcrops and boulders of Artubi, a ridgeline between two geologic units at Jezero.
Did you say Artubi?
Artubi is what they nicknamed that region.
After R2D2
I don't know.
or something?
It's Artuby. I'll have to look up what it's named after.
And did you say geological units?
I did.
That was my nickname in college.
Geologic unit.
What?
That was your nickname in college?
No, it wasn't.
Geologic unit.
What does that mean?
Like in geology, you refer to different two places with different histories. It's different geologic units.
Cool. Yeah.
So on a map,
not units like seconds and meters.
Right. No, of course not.
On a map, they'll have different colors.
Right.
Geologic map.
Yeah.
So that's good. It's exciting. They got their first sample, so they'll be able to do some more. And I think Ingenuity actually had another flight recently too. So that was exciting.
The helicopter has far exceeded its original
been zipping around
plans. Yeah. Right. Yeah.
And then going the other way, well, actually, I don't know where Mars is right now. So maybe it's going the same direction from Earth to the sun.
Oh, yeah.
I don't remember. There's a bunch of active sunspots on the sun, and they're pretty big.
Where are we on the cycle right now?
On the infamous solar cycle?
We were at the crazy minimum for so long, and now we're starting to ramp up. So we think the new solar cycle has started.
Okay. So solar max is ahead of us, and solar min is behind us is where we are.
Yeah, we're in solar cycle 25.
Okay.
I think officially now. Right. There was some hedging about when it was starting, but they think it started. And these are two pretty massive sunspots. If you have a telescope and it's safe, you have solar
with
filters
the appropriate
and stuff.
filters. Yeah.
You can actually see these. If you did the pinhole camera thing where you did a little pinhole thing
and project it, you can see
the
them.
I think you might be able to see them. They're really big.
That would be impressive.
I did make that part up, but you can definitely see them with telescopes.
I do have filters for my binoculars from the solar eclipse of a few years ago.
Nice. You should be able to see it.
I might check that out.
They're quite large.
Yeah.
Binocs are tough. I guess you just have to lean them against something to steady them.
Yeah.
Yeah. There was a little solar flare from one of the smaller ones, but these two big ones just rotated in to where they're facing the Earth for a couple of days. So if there's any sort of energetic events for the next couple of weeks, it'll be directed at us.
Nice. So. We have Jupiter and Saturn up in the night sky, and I took my telescope out and managed to get a glimpse.
Good job.
And Jupiter's pretty impressive.
Can you see the stripes with your telescope?
Can see the stripes. Not at the time I looked, which I'm hoping is because it was on the other side and not because my eyesight is too poor. But in the 4 Galilean satellites quite clearly. Nice. And then with Saturn, you could see the rings and Titan quite nicely. So
wow.
Very nice.
Speaking of things planetary.
Mm-hmm. We do that sometimes.
You remember the story of Egotron.
Egotron.
As I like to refer to this putative object out in the outer solar system in the Kuiper Belt. So this is linked to the long and tiresome story of whether or not to call Pluto a planet. So we won't talk about whether or not to call Pluto a planet.
No.
But the discovery of bigger things than Pluto is sort of what kicked that whole business off. And Mike Brown, whose Twitter is, what's his Twitter handle?
Pluto Killer.
At Pluto Killer, discovered an object comparable in size to Pluto in the Kuiper Belt.
Eris,
Eris or Sedna, one of those. Yeah. Mm-hmm. Anyway, he styles himself as the person who dethroned Pluto from its planetary status instead of being happy that he found the 10th planet as Eris or Sedna or whatever. But now he's decided that he wants to be the person who's found the 9th planet with, and it's actually the observation and the study they're doing is very cool. They're looked at the orbits of objects in the Kuiper Belt and found that there's an uneven distribution of the alignment of the egg-shaped or elliptical orbits of several of these distant objects, which suggests that they're being gravitationally perturbed by something with a fairly hefty gravity out there. That a lot of, with Konstantin Bagatin at Caltech, they did a lot of sophisticated analyses of the data to make sure that they weren't having any biases in their analysis, and then also a bunch of numerical simulations and body simulations where to say, okay, can we get, if you put a massive thing out there, does it sort of shepherd the alignment, move the orbits of these other things around or rotate them around so that their orbits are aligned in a certain way? And it was, a very plausible story. And,
sure.
But this thing is big. It's very far. It's big, but it's very far away from the sun. You don't know exactly where it is. It's going to be very, very faint. And so we don't have a direct observation of it. So the Egotron part of that, as they like to call it, Planet 9, or you might like this, Jim, P9.
P9.
It is very P9.
It's P9. And so they think they've got the biggest P9. And it's they call it the most planetary of planets.
What does that even mean?
I don't know.
I think you might have a rant coming here, but I also have a different rant.
I feel like the Earth is pretty planetary as planets go.
Which is? The Earth. Yeah.
So I'm betting. So let's say this thing. So first of all, you're maybe going to rant about the small number statistics thing, yes?
No.
No?
No.
Oh, I was going to rant about that also.
Go ahead.
Oh, good.
No, that's multiple rants. First of all, this idea is based on like 6, 8, 10, 12 objects or something like this.
Well, this new paper, the reason we're talking about it today is because there's a new paper with a broader survey.
Right, but it's still not that many, and I think a lot of planetary scientists are still quite a bit skeptical about this. But anyway, I won't rant about that.
That's true.
But I will rant about this. What if it's real?
Okay.
If it's real,
yes,
I bet it's still not a planet.
Why?
It's not a planet by
the stupid definition that
the IAU came up with.
Yeah,
that's right.
Because its orbit will be huge, something like 400, 350 AU or something like this, right? There's no way it's cleared that orbit.
That's right.
And therefore, doesn't matter how freaking big it is, it's not a dang planet. It's not Planet 9. It's just another dwarf planet.
It might still be P9.
That's the beautiful irony. That's the beautiful irony of this whole thing. is that the discovery of big things out there led the IAU to come up with this definition of a planet that is a coupling of how big it is and where it is.
Yeah.
Right.
And the farther out you are, the bigger you have to be in order to be a planet by that definition.
Right. And at those distances, it almost doesn't matter how big you are. You can't possibly...
Unless you're a star.
Right. That's right.
That's true. I hadn't thought about that particular aspect of things. But they have updated their calculations with... of their observational biases, and they find that the clustering of these egg-shaped orbits is still statistically significant at the 99.6% confidence level.
It's pretty okay.
Which is pretty good.
How many sigmas is that?
That's what I always thought was funny. It was like, and I was thinking, it's spoken like a true high-energy physics particle guy, where 5 sigma is the gold standard.
Right.
And 99.6 is not 5 sigma. No. Somewhere in the 4 sigma realm.
Okay.
Only 4 sigma.
But at the same time, it's like, I'm totally willing to believe that there's some biggish thing out there,
Yeah.
And it's very cool if they've been able to identify its sort of general neighborhood from the study of the orbits of these other things.
I wish they could make some better predictions about so we could predict generally where its orbit would be and generally what it looks like, but there's no predictions about where it would be in its orbit that would help us actually look for it
right
in a certain
now.
place.
Right.
Yeah. And so even if yeah.
Yeah. So the speaking of the orbit, semi-major axis, which is the average distance from the sun, is 380 plus or minus about 100 astronomical units.
Oh, sure.
So about 400 times further from the sun than the Earth is, and about 10 times further than Pluto is. A somewhat
New Horizons
eccentric
will
orbit.
get there when?
Yeah. And the mass, about 6 times the mass of the Earth. So smaller than Uranus and Neptune.
Right.
And as you said, Jim, out there's just all kinds of stuff. It hasn't had time. And this is one of the criticisms of that new planet definition.
Terrible.
Is that if you took this object, P9...
and you put it where, Josh?
And you put
Careful.
it where it wants to go, close in to the inner solar system. Then it would be a planet by the IAU definition. Sure. But out there in the boondocks, it's not a planet by the IAU definition, which
another interesting
strange.
thing to think about, right, is that if you're out at 300-ish AU, right?
Yes.
We have this debate sometimes about the Voyager probes. And they're at the edge of the solar system.
Oh, right.
And they're at 150 AU.
Right.
And they're
outside the
heliosphere. So this planet would also be outside the heliosphere.
Right. Yep.
I would actually, it's funny how much we've talked about this Planet 9 thing, but it would almost be shocking if there weren't some objects like that in our solar system. I mean, in any early solar system, there's going to be stuff that gets flung in and out.
Yeah.
And
I mean, there's a question of what is the biggest object to get tossed out?
Right.
Mm-hmm.
Right. Because this thing probably did not form out there.
Oh, yeah. It probably formed somewhere in the Uranus-Neptune type of area and got flung out because of Saturn or Jupiter's gravity.
It was a Uranus wannabe or something like that.
Right.
Then there was some sort of annular event.
Yeah. I mean, we don't have any planets like this in our solar system, but there are plenty that we've seen in exoplanets. Well, right. There are no planets in our... In the planets that we know of so far.
I just thought of 9 inappropriate things I could have said about where P9 wanted to be.
But these kinds of things are something that far out. We also are not going to be able to really detect around other planetary systems yet.
Right.
Because they're going to be too far out, unless they're things that are formming in early planetary disks, where we sometimes do see things forming really, really far out.
But then But then
it's
they're probably much more massive than this thing.
They're much more massive, and because
6 Earth masses.
It's only 6.
6 Earth masses.
That's a teeny thing.
Yeah. That's in the realm.
That's in that realm. We've seen a bunch of exoplanets.
We've seen exoplanets with that mass, and
Neptune,
Uranus, and Neptune went through that mass en route to becoming our good buddies that they are today.
Yeah.
So in any event, it's still, and as you say, Jim, it is still small number statistics, so you can rant on that. There's on the order of a dozen objects, orbits that they're.
I have a hard time. I mean, like, again, these guys are very smart folks, and I don't want to but like. I think there are a lot of astronomers smarter than me who still think it's fishy to make such a conclusion based on such small numbers of objects. There could easily be some observational bias that they're not. They claim to have taken care of all that and say it's 99% or 99.6%.
To play the devil's advocate, if you imagined an extreme case where there are 361-degree slots for something to be, and you find 12 objects and 11 of them are in the same one, you would say something's going on here.
You would, but you might say that's because I've only looked in that direction. Right,
which is what some other smart astronomers took some other data and said, well, we don't find such a compelling argument. And this paper, the whole point of this paper, and then we'll put this to bed, is that they did a more thorough analysis of all the observational biases and claimed that the sort of rebuttal papers were too insufficiently broad or not correctly.
This is the fun part of science where there are rebuttals to the rebuttals.
Yes.
Yeah.
All right. The iterative process of science.
That's the way it works.
On board.
That's
I have to say,
we need to see more things out there.
The plots in this paper, though, I'm just like, what? That's this? Some of them.
They have nice colors.
That's true, but some of them are just some squiggly lines.
If they have nice colors,
dots.
I'm convinced.
Yeah. They do some interesting like probability density plots that are maybe compelling.
Yeah, but it's just, it's that thing with statistics, lies, and whatever. I mean, like, it's just, it can be easy to manipulate statistics to say what you want. Obviously, we're trying very hard in science not to do that, but it's sometimes if you've decided Planet 9 is out there. Anyway.
Yeah. Well, we need to see more objects in the distant part of the Kuiper Belt and see whether their alignment is.
So we need. So isn't it okay? We really kind of need a more big, broad sky surveys, and I think there's one coming online in 2023 or something like that with the Vera Rubin telescopes in Chile that's going to be doing that. So that's we have a good opportunity to learn more about this and to maybe confirm this existence.
All right. Well, on that note, let us trivia transition to our galactic story with a galactic trivia.
Ooh.
Depending on
it's so wrong then.
Depending on how you define galaxy exactly in our local group, this is sort of a
particular annular.
Right. In our just as a pre-trivia question, about how many galaxies are in our local group?
Dozen-ish.
Yep.
Yes, a few dozen, depending on exactly how you count or who you talk to. But the local group is not cosmological in scale. In other words, it's not expanding due to the expansion of the universe.
Correct.
The smallest things that are sort of expanding due to the expansion of the universe are called superclusters.
Superclusters, right.
So our local group is in a supercluster, and then there's some...
It is pretty great.
Then there's some argument about recently whether our supercluster that we used to call the Virgo supercluster, or is it part of a bigger one called the Laniakea supercluster? But we're going to stick with the Virgo supercluster.
Okay.
And that one is cosmological in the sense that it's expanding with the expansion of the universe. In other words, its mass density is like, I'm not expanding with the expansion of the universe, just with old age.
And Oreos, in my case.
Right. Well, so we're not expanding because the universe is expanding. You have to be very big and diffuse to be carried away that way. And how big? A supercluster big. So the question is, how many galaxies in the Virgo supercluster?
Mm-hmm.
There's a few dozen in our local group cluster, which is part of this supercluster. How many galaxies, give or take, in the supercluster?
More than a few dozen. Spoiler alert.
In our supercluster, more than a few dozen. Right. And speaking of galaxies, we have a story about a peculiar kind, neither lenticular nor
this just, I guess this would fall under your favorite branch, the irregular. Pretty much everything that's not a spiral or elliptical galaxy will put in that catch-all category of irregular galaxy. And the most common type of irregular galaxy are dwarf galaxies. I mean, there's lots of small galaxies. And in fact, when you say there's a few dozen galaxies in our local group, really only like 3-ish of them are significant. Significant. It's us and Andromeda and like one other spiral galaxy, right?
I think there was recently a Netflix show called The Irregulars. They didn't get a second season.
Did it have to do with galaxies?
No.
Damn.
Sherlock Holmes or something.
But most of those members of our local group are just these dwarf galaxies. So, we have a couple of nearby neighbors that you can see with the naked eye if you happen to live in the southern hemisphere.
Which many of our listeners do.
Which many do.
You lucky southern hemisphere.
I know, they get to see really cool. I mean, there are cool things here. But the Magellanic Clouds, right? There's a small and large Magellanic Cloud, which are, like I said, visible to the naked eye. And they're irregular galaxies, but they are irregular galaxies that have a lot of action going on in them. There's lots of star formation and star death. In fact, right, the most recent supernova that we saw, supernova 1987, happened in the Large Magellanic Cloud. There also seems to be this group of galaxies called these
ultra diffuse
galaxies. These are galaxies with that have a very low concentration of stars. The stars are kind of spread out over a huge area.
They're pretty diffuse.
They're very diffuse, as the word. Ultra diffuse even.
Interesting.
Curious.
So they're very spread out.
They're very spread out. And we've wondered a while about how you would make a galaxy like this. And some of them, the primary way in which you'd make a thing like this, they're diffuse because they're not making lots of new stars.
Right.
So if you're making new stars, there's going to be lots of light associated with those new stars. These are diffuse. Studying these things, by the way, is tough because they're so diffuse. They're next to impossible to know they're even there, right? They just, even if they're in our local group, they're going to be hard to see. And if they're farther away than that, they're going to be next to impossible. So studying this is tough, but we have found some of them, and some of them are just like off on their own, these ultra diffuse galaxies out in the middle of nowhere, and we wondered what the hell is going on there.
Not you mean on their own, unlike the Magellanic Clouds, which are sort of
they're just kind of satellite galaxies of our Milky Way, exactly. And if you see beautiful pictures of Andromeda, it's got some satellite galaxies hanging around it and stuff like that. Those galaxies, you can make those things ultra diffuse by stripping away the gas. Right, the gas and the dust is what makes stars, and so if you strip that out of a galaxy, you can have an ultra diffuse galaxy. But it's hard to imagine how you do that for a galaxy that's all by itself, because the way you'd strip gas out of a galaxy is collide it with another galaxy. Right, and so what these people have been doing is running these very complicated computer simulations and seeing if in their results the physics gives them ultra diffuse galaxies that are sitting by themselves, and it turns out can make them.
Okay.
And the way you make them is basically what I just said. You collide them with other galaxies, but you collide them in such a way that they have enough speed to get the heck out of the area.
So the stars plow on through.
The gas kind of smacks into the gas of the larger galaxy and gets accumulated into the larger galaxy. And now I have... So what you should have left is stars and what else?
Gas.
No, you strip the gas away by gas. The dust is gone. The gas is gone.
Right.
You're left with stars and
gravity.
Dead stars.
Not dead stars.
Dark
matter, right? Because dark matter also does not interact with itself very much, right? The gas, when big clouds of gas hit each other, they smack into each other. The stars are so, in even a regular galaxy, they're so diffuse that they don't hit each other, and the dark matter also goes through. So these galaxies carry their stars and their dark matter, and then if you wait a long time, the stars become, the big stars burn out and die, and you're left with just a bunch of dead husks and a diffuse bunch of stars and some dark matter. And that's exactly what they saw in their simulations. And the great thing about simulations is
you can make them do whatever you want.
That's right.
You can do whatever you want. No, but you can run them until what you see in the simulations matches roughly what you see out there, and then you can run them back and see where that came from, right?
Yeah.
The trouble with the real universe is I go out there and see what I see, and I can't make time go backwards to see. I know this is very, it's a frustrating part about astronomy is that sometimes it's and this is
the frustrating part about astronomy. You can't make time go backwards.
Can't make time go backwards. Yeah. That's the only frustrating part.
Yeah.
Well,
also unique to astronomy.
And yes, it's not frustrating for anybody else to not be able to make time go backwards.
It's particularly frustrating in astronomy. I mean, all these things happened billions of years ago.
That's true.
We get in the mail. We get these quack things that are like, since you weren't there, it might as well be 4,000 years old rather than 14 billion years old or whatever like this. And so it's frustrating because you can't directly show. Anyway.
Yeah.
But in a simulation, you can run the simulation back in reverse and see if I'm getting these ultra diffuse galaxies, where did they come from? It turns out they came from these collisions long ago, and the things got flung out, much like, what are the names of those? Borisov and whatever. those interstellar comets. Those things, I mean, obviously very different scale things, but those things get flung out of their solar systems. These are galaxies that got flung out of their groups long ago and had the galaxies, the gas stripped away by collisions within their group. Then they got thrown out of their group, and now they're there.
Right.
So,
pretty cool.
So I learned a new term with this story, which is that they're
annular galaxies.
Quenched.
Oh, quenched.
Some of them are quenched.
Which basically means star formation is stopped, which is
because they don't have the fuel for it.
No more raw ingredients to make new stars.
Yep.
Over the age of the universe, in general, there's a decline in the rate of star formation in all galaxies.
Yeah,
right?
you bet.
Is it monotonic? I mean, was there a time when star formation was increasing in galaxies in general for the first, I don't know, n million or billion years of the universe, and then it turned over and started decreasing? Or did it like, bam, we've got the maximum star formation rate essentially right at the beginning, and it's been declining ever since?
I think the latter is closer to it. I mean, certainly you had to start star formation, you had to reach a certain, the conditions had to get right for that. And so at absolute first, when the conditions weren't quite right, a few stars would have formed. So there was a little bit of a ramp up, but I think in general that ramp up was pretty quick, and then fairly
astronomically it's a small amount.
Yeah. Right. So we've basically been the universe has been in a declining state of star formation.
That's right.
Since it started making stars.
But don't worry.
It's all been going downhill.
It is sad, but don't worry. We have plenty of time left. There's still tons and tons of gas out there. But if you wait I don't know how long you wait, 100 trillion years or something like that, we're going to be in real trouble.
Hey Siri, set a reminder.
Do we really have to wait 100 trillion years before we're in trouble?
Well, we're in trouble
for other reasons
before that. But I think that star formation will be at a minimum or essentially done in 100 trillion or 10 trillion, something like that. Those are very different numbers, of course, 10 and 100
so
trillion.
Just like with our exoplanet stuff, future telescopes that are coming online, like LSST, the Large Synoptic Survey Telescope, and I think there's one called the Roman Space Telescope. Ooh. Those are going to be able to observe sort of these diffuse, lower brightness things and hopefully detect more of these objects in the future.
Yeah. Yeah. I mean, it's cool because even though, I don't know, you might say who cares about those galaxies, but they're telling us about galaxy evolution and how the universe as a whole evolved, which is fun.
Right. I'm still somehow I'll get over it, but I'm obsessing about the decline in star formation.
Oh yeah, no, I know. That's going to keep you up at night. You're going to get upset.
That's going to be the next thing that I'm stressing about. Let me just ask if you know the answer to this. We haven't talked about it before, but is the 5 billion years ago was the star formation rate twice as big as it is now, or 5% bigger, or 10 times bigger?
I don't think I don't. I'd be talking out of my butt if I said I know what the answer was. Okay. I want to say, 5 billion years is enough time that the size of the universe was, the expansion of the universe had an effect on star formation rates in the sense that, star formation is often...
Let's just take the Milky Way. So forget about expansion.
Right. Okay. So if I forget about
the Milky Way galaxy.
Yeah.
And the star formation rate in the Milky Way is lower now than it was 12 billion years ago.
For sure.
And I'm curious to know, and we can come back to this in a later episode.
We'll have to, because I don't know the answer.
I'm curious to know, 11 billion years ago, was it forming stars 10 times faster than it is now? Mm-hmm. And 10 billion years from now, will it be 1% or 10% or 90% of the current level?
Yeah, I feel like the slope is not so high. I feel like it's a fairly low sloped thing.
Maybe initially it was high and it's sort of tailing off.
But yeah,
the thing is, when you make a big star, which has a lot of stuff in it, it burns out super quickly.
Right, and then it blows up, throws the stuff.
Right.
So you're losing stuff by locking it up into small stars. But there are a lot more small stars than there are big stars.
But once you make those small stars, they stick around forever. They don't recycle that material, so you don't make new stars with that material ever.
Right,
basically.
Right.
Yeah, especially because they don't blow up anymore.
That's right.
They'll never blow up.
Yeah. Nope. Just stuck with them.
All right.
Till they're husks.
Well, speaking of numbers then, let's go back to the local supercluster, the Virgo supercluster.
Okay.
And maybe, I don't know if we call it our supercluster.
Yeah, we didn't leave it technically.
We haven't left it. how many galaxies, give or take, would you say are in the Virgo supercluster of galaxies, our home supercluster?
Addie?
Do you want me to go first because you know the answer?
I don't know the answer, but
I
you
am
can go
going
first.
to hypothesize that the number is 67.
67?
Yeah.
I already told you there's a few dozen in our local group.
You want me to guess? Okay.
There's a few dozen in the local group, and the local group is not expanding
Correct.
cosmologically.
True.
You have to go to a supercluster to be expanding cosmologically.
Yeah. Okay.
So that's my...
I'll take back my answer
That's my Peter Sagal,
and go with
don't tell me, hint mode there.
163.
Okay.
I think it's a few tens of thousands.
Oh,
I'll go
I
with
like our orders
20,000.
of magnitude difference.
Yeah. You're right, Jim.
Oh, good job.
About 50,000 ballpark.
Wow.
Yeah, it's a big mother.
I assumed my number was wrong, but I had no idea. So
A few years ago, some researchers decided that we were actually part of that the Virgo supercluster is a piece of some larger thing called the Laniakea supercluster, which is about twice as big in terms of number of galaxies. But since it's part of the universe that's expanding cosmologically, I kind of think it's sort of arbitrary, right? You normally define a cluster as something that's like
Gravitationally
cohesive,
bound, right?
Right. Yeah.
Right.
But if it's all spreading out anyway,
that's sort of like a question I have for these ultra diffuse galaxies.
where's the edge of the galaxy?
Well, how do you define the edge of the galaxy, and how do you define what's the edge between an ultra diffuse galaxy and like
Intergalactic space.
something else with some stars?
Right. Well, those ultra diffuse galaxies are kind of like little island things. I mean, they're out in the middle of intergalactic space. There's a few million or a few tens of millions or hundreds of millions of stars, and then nothing.
Okay.
So they kind of
see them,
are
but
well
there's
defined,
just
and they
a
are
lot-
gravitationally bound. Even though the stars are spread out, they're a gravitationally bound thing, a bound system. Your supercluster thing is interesting. I mean, like, how do you?
What's the definition?
Yeah. And
Where's the edge?
we have fun questions like what's the largest structure in the universe or something like. Well, it's ill defined because we have these great voids and stringy structure in the universe that is made up of like a bunch of superclusters connected. Is that a structure?
Right.
Is it a
Or
smiley
not?
face?
Because it's not gravitationally bound. Right. Is that really a structure or is not? Not. I don't know. These are good questions.
One of the interesting things that sort of talking about how you characterize these things, so and it's a quantity that I hadn't encountered before, is the mass to luminosity ratio of something. So you take the sun. Its mass is one solar mass.
And its luminosity is one solar luminosity.
You read my mind. So that ratio is 1. What is the mass to luminosity ratio of the Virgo supercluster in those same units?
In solar units?
And yes.
It's also 1.
A reasonable guess, but
No,
42.
Yeah, it's much larger than 1. A few thousand.
Yeah.
you're in between. I'm going to give it to Addie. 300.
300. Okay.
Yeah.
Okay. I was close to not going over.
Yeah. And part of that's because of dark matter,
Part of it is dark matter. Part of it is
which has
just
no luminosity
gas and dust, which
is a significant chunk of matter.
right.
Yeah. For the Milky Way galaxy, it's about 64, which is close to 42.
Yeah, not bad.
Yeah.
Yeah, that's what I was thinking of.
Yeah, it must have been thinking of the Milky Way, right? Yeah. Well, while it may have felt like the time astronomers have been arguing over the definition of a planet, it was just another episode of Walkabout the Galaxy. Perform a review of us as a special end credits sketch for the next MCU movie.
Okay.
Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel where you can see most of our episodes, some of our bloopers, which in today's episode's case is one and the same thing.
I thought we were going to cut that.
And all of our music videos. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG or just email wtg@ucf.edu. Our theme music was composed by Richard Jerusik. Production assistance was provided by Diego Rodriguez. Thanks to our listeners in Vermont and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
And I'm Jim Cooney.
We're the astroquarks signing off until the next episode of Walkabout the Galaxy.